Warm greetings to Professor Gloria and all my classmates in the Analytical Chemistry course of the Chemical Technology program. My name is Sebas and my partner is Sara.
Today, we will present the analysis and experimental recreation based on the article Teaching Electrochemistry in the General Chemistry Laboratory through Corrosion Exercise.
This presentation aims to demonstrate how electrochemical principles applied in real-world applications through the destructive phenomenon of metal corrosion. To structure this video, we will define corrosion, detail the methodology of our specific experiments, analyze mass loss data, and conclude with our findings and cathodic protection.
Corrosion is an electrochemical process in which a metal loses electrons and degrades through interaction with the environment. This phenomenon occurs due to the spontaneous formation of the galvanic cell, where the metal acts and an anode undergoes the oxidation. On industrial level, corrosion represents a significant problem as it affects the pipelines, metal structures, chips, industrial equipment, and transportation systems. Understanding corrosion involves studying concepts such as redox reaction, reduction potential, electrolytes, pH, and electron transfer. This presentation analyzes these principles and their experimental application in the laboratory.
In our experiments, we explored different types of corrosion. First, we examined uniform corrosion, in which the entire surface of the metal deteriorates evenly. Then, we studied galvanic corrosion, which occurs when two different metals are in electrical contact in the presence of an electrolyte. We also analyzed corrosion due to oxygen differences, which is very common in submerged structures such as ship hulls. Finally, we studied corrosion in acidic environments, where the presence of hydrogen ions accelerates the process.
Two different metals are connected. Zinc will act as the anode and copper will act as the cathode. Both are first immersed in distilled water and then in salt water. A multimeter measures the voltage and the current between them. What is this done? To demonstrate how the presence of electrolytes, ions in solution, influence the flow of electrons and therefore corrosion. Distilled water conducts almost no electricity, low corrosions, and salt water has many ions, increasing the electrochemical reaction, more corrosion. Using phenolphthalein turns pink at a basic pH. As OH ions are produced of the copper zone changes color, like visual evidence of reduction. So finally, in distilled water, very low flow rate is low corrosion. In salt water, high flow rate, zinc corrodes faster.
Experiment 2. Influence of oxygen concentration. What is done? Two zinc sheets are placed in the same sodium chloride solution. Ice bubbles around one of them using a pipette and the voltage between the two sheets is measured. Why is this done? To simulate how different oxygen levels affect corrosion in real structures like ships, pilings and submerged pipes. Where the metal has more oxygen, the oxygen is reduced faster, so that area becomes the cathode and is protected. Where there is less oxygen, the metal tends to oxidize, making the area the anode, which corrodes. This creates differential oxygen corrosion, very common in marine environments. Electrochemical process. Oxygen gains electrons and forms hydroxide ions, so that region doesn't corrode. Zinc loses electrons and forms Zinc plus 2 ions, and this is the corroding area. An increase in voltage between the plates shows that an electrochemical cell has formed due to the oxygen concentration difference. Final result: The plate with bubbling is protected, while the one without bubbling oxidizes more quickly.
Corrosion in acid and sacrificial anode. What is done? The following are placed: an iron nail, a zinc chip, and 3M hydrochloric acid, which accelerates the corrosion. First, they are tested separately, and then they are connected to each other with a wire or clamp. What is this done? To demonstrate the function of zinc as a sacrificial anode, a fundamental principle of galvanic protection. In the process without connection, both curve, but the zinc curves much faster, and the iron also reacts with the acid, releasing hydrogen. And in the process with electrical connection, new both metal from a galvanic cell. Anode zinc curve more, and cathode iron is protected. This occurs because the zinc has a more negative reduction potential, and that it oxides more easily.
Experiment 4. Cathodic protection by impressed current (ICCP). What is done? A 9-voltage battery is used to electrically force the protection of the metal. Connections: negative terminal iron, positive terminal zinc. Why is this done? To demonstrate how industry protects large structures such as ships, long pipelines, underground tanks, offshore platforms. The ICCP systems protects metals by controlling the applied potential. Induced electrochemical process. The metal receiving electrons from the battery becomes the cathode, does not corrode. The metal connected to the positive terminal becomes the anode, thus corrode. Key results: the iron almost completely stops corroding. The zinc shows heavy bubbling and accelerated corrosion. The multimeter shows higher current due to the externally applied force.
Turning to the analysis results, we begin with the ionic kinetics. Experiment 1. Table 1 shows the current flow measured in the zinc and copper galvanic cell in two media. While in the still water, the current was practically zero. In the 0.5 m NaCl solution, the flow rose to 18 microamperes. This disparity proves that thermodynamics predicts the reaction. It is spontaneous, but the kinetics are limited in the conductivity of the electrolyte. The appearance of a deep pink color of the copper electrode upon the addition of phenolphthalein verified of the cathodic oxygen reduction reaction. This increased the pH due to the production of OH is a direct visual confirmation of the electron flow. In the experiment 2, the differential Hertzian cell gave us a delta of 0.12. This voltage generated between two identical metals is evidence of the dependence of the cell potential on the oxidation concentration, as predicted by the Nernst equation. The area with bubbling oxygen became polarized to the more positive potential, acting as a cathode, gaining electrons, while the oxygen-deficient area became the anode, losing electrons, undergoing corrosion. This concentration difference is the main driver of corrosion in civil and naval structures.
Experiment 3 is the central piece of the study. Protection by sacrificial anode. Working in an acidic medium where corrosion is accelerated, we compare the mass loss of the iron alone versus iron coupled with zinc. Table 3 is conclusive. Unprotected iron lost approximately 0.065 grams. When coupled to zinc, the mass loss of iron dropped 0.004 grams. This represents a protection efficiency greater than 94%. The explanation is purely thermodynamic, since the reduction potential of zinc (-0.76 volts) is much more negative than iron (-0.44 volts). Zinc acts as a consumable anode. It preferentially loses electrons. forcing iron to remain in its oxidation state zero. In other words, it cathodically polarizes the iron and prevents its corrosion. Finally, experiment 4. Verify the impressed current cathodic protection or ICCP system. When iron was alone in acid, we observed vigorous H2 bubbling on its surface. After connecting the negative terminal of the battery directly to the iron, the bubbling completely stopped on the iron surface and shifted to the auxiliary electrode. This external current reverses the natural polarity of the iron, forcing it to become the cathode and stopping its oxidation.
The rate of corrosion is limited by the ionic conductivity of the medium. A high concentration of salts in electrolyte increase the ionic mobility, results in the great current flow and therefore drastically acceleration corrosion, even if the thermodynamic driving force is similar. Corrosion can be driven by environment factors. A difference in dissolved oxygen concentration creates a concentration cell, generation of electrical potential. The area with the lower concentration becomes polarized as an anode, while the area with the higher concentration becomes polarized as a cathode, is protected. Cathodic protection is the most effective method of stopping oxidation. This is achieved in two ways. Sacrificial anode, galvanic, clumping with a more active metal achieves superior corrosion reduction, and ICCP, applying an external source, reverses the polarity of the structured metal, forcing it to become the cathode and stopping spontaneous oxidation.